Okay, we are ready for our next talk. Our next speaker is Professor Yuval Roichman from Bar-Ilan University, and he's going to tell us about cyclic descent extensions and higher Lie characters. Professor Roichman.
Okay, thank you. And thanks the organizers for doing this great work and during these difficult times, and for renewing the in-person conferences, which is great for us and something, a very successful conference, and to see all young people coming into the field, it's for me, it's making me very happy. Okay, so we will speak about the cyclic descent extensions and higher Lie characters. So the talk will consist of two parts. First part, I will try to explain the concept of cyclic descent extension. I apologize for those who heard this part for me many times, but many people are not familiar with this. And the last part will be to explain in brief what are higher Lie characters and how do they play the role in solving problems from this field. And the middle will be the main result. Okay, so it will be short, just to one slide to present the main result. Okay, let's start. So we start with the descent set of a permutation with just the set of positions where the value decrease. And this is very classical. Some people trace it back to Euler, even so I'm not sure that Euler, the generating function was studied for sure by Euler. And the cyclic descent was defined by, let's say cyclic descents are descents, but we also compare the last position, the value of the last position to the first one. So n could be a descent. These are cyclic descents. They were introduced by Klyachko in '74 in a paper about Lie algebras, which was ignored by the community of algebraic combinatorics. But then in the 90s, there were two papers of Cellini that picked attention, and there are many follow-ups of these papers of Cellini that introduced cyclic descents in the context of cyclic descent algebras. Anyway, okay. So, and there are descents and cyclic descent, there are descents of standard Young tableau. So they were, I suppose they were introduced by Schutzenberger, or maybe he was the first to realize that RSK defines naturally descent set on a standard Young tableau. If it's not Schutzenberger, please correct me, but anyway, so what are descents? Descents are where I is in I plus 1 is in lower row than I. For example, here, 1, 2, 2, 3, 3 is down, 3, 4, 4, 5. So the value here, 2 is a descent, 4 is a descent. So the descents here are 2 and 4. So while in permutations we look on positions, on tableau we look on values, and there are good reasons for this, not to be mentioned now. Anyway, while it was very natural to define cyclic descents on permutations, comparing last positions with first position, it could be bigger or smaller. Here, n could not be in a higher low than 1. In any standard Young tableau, 1 is in British way of writing, 1 is in the first row, so n could not be cyclic descents. So this was the first problem that was discussed with Vic Reiner, Onadin, and other people, but it was discussed before by Brandon Rhodes and others, we will see. Define a cyclic descent for standard Young tableau of any shape lambda. Okay, so cyclic descent set for any standard Young tableau, I plus n could not be in a higher row than 1. So we should see what are the properties what are the important properties of descents that the cyclic descents that we would like to see in Young tableau? Okay, let's look at this sequence. This is series of shifts of rotations. So 3, we shift the permutations. 3 would be in the first position. Now 4 is in the last position. Now first position, so etc. etc. And so this is there are 5 permutations in this orbit of cyclic shifts or rotations of permutation. And the descent set is not so clear what's going on with descent set, but with cyclic descents, okay, we see the red letters are where the cyclic descents are located, and you see 2, 3, 5, 3, 4, 1, 4, 5, 2, etc. You see that a shift, rotational shift of the permutation shifts the cyclic descent. So this one property that we would like to see. And also another property that if you take off, if we delete the letter n, we recover the descent set. So the cyclic descent set of this, of rotation action on symmetric group satisfy first, if we delete n from the cyclic descent set, we recover the descent set. And second, there is a rotational shift that increase the values of this descents by 1. Okay, so there was a work about this by Brandon Rudd, pioneering work like 12 years ago, about Rudd proved that there exists a cyclic descent map on standard Young tableau of any rectangular shape, such that if we delete n, we recover the descent set. And Schutze-Berger, Joux-Detecken promotion that was mentioned in previous 2 talks shifts the cyclic descent set by 1. Okay, good news. So motivated by these results about Cellini, about symmetric group, and Rods about standard Young tableau, we defined an abstract concept. Oh, let's see an example of Rods. So this is, you see the promotion, we have seen it. So you start with this tableau, you end with this tableau. And here you see the descents are 1 and 4. Here the descents are 2 and 5. So this was what we would like it to be. And you see here are the tableau. These are the orbits. This tableau is mapped to this one to this and back. And here we should ad hoc add 6 as a cyclic descent. Why would not explain now. And here we should also add 6. You see 1, 3, 2, 4, 6. And so these are 2 orbits, and the, let's say, generalize the abstract concepts. Okay, given a set of combinatorial objects T and a map, descent set map that map any element to a subset of n-1, the cyclic descent extension contains a map. Any element has associated subset of 1 to n, not of 1 to n-1, but 1 to n, and a bijection, which should be a rotation or promotion on the set, which shifts the cyclic descent set. And if we restrict it to first n-1 letters, we recover the descent set. Surprisingly, there is here a third axiom or property, which is not so transparent at first glance. And this is non-Escher property. The cyclic descent set of T of an element could not be the full set or the empty set. And why? Why we call it non-Escher? This is because of the Escher famous drawing. I don't know how well you see it. that illustrate the fact that you can never walk up forever or walk down forever. This is a moral for life. If you are down, know that there is a point you will go up. And also if you go up, remember that you will sometimes go down. You cannot go up. And this illustrates the paradox of permutation cannot have Cellini cyclic descent set, empty set or full set. And also in words, if you take all rectangular shapes except of one row or one column, then this is a good illustration. So these are two examples for this. And why do we need the third axiom? The third axiom gives rigidity for the theory. For example, the cyclic descent set distribution is unique, is defined uniquely. It's not, the cyclic descent extension is not unique, but the distribution of cyclic descent set is unique. And this is thanks to this. Also, all connection to representation theory that some of them we'll see later, some not, are thanks to this axiom. Without this axiom, we are in a zoo. Okay. So, okay, what is the answer for standard Young tableau? The answer for standard Young tableau is that these are called hooks, hook shapes, one part bigger than one, and the set of standard tableau of any given shape has a cyclic descent extension if and only if lambda is non-hook. And the proof that we had with Vic Reiner is algebraic. It involves Postnikov-Toric Schur function and Gromov-Witten invariance. We can say more, it involves some positivity properties of Postnikov-Toric Schur functions under certain substitution specializations, simple specialization. But this is important because if the positivity say that there is a combinatorial realization. If there is no positivity, no combinatorial. There is something abstract maybe, but not combinatorial as we want it to be. And now there is a second proof given by Bryce Wang, purely combinatorial proof, and this proof is in, I should make some add to this, because I think he was a very talented student in MIT and shifted to theoretical computer science, so people do not know of this. So this involves twisted Schutze-Berzé promotion for any shape and skew shape. And what was Tom Robbie told us that very few shapes are behave like coherent with Schutze-Berzé promotion. For the Bryce Wang, all of them are coherent up to, let's say, you'll see, his paper is long, and this is some conjugated or twisted Schutze-Berzé promotion that at least it gives a combinatorial proof to this statement, and he shows that Rhodes, for example, is a special case of his promotion. Like for rectangulars, the Wang promotions is the Schutze-Berzé. Just okay. Question?
This theorem, is it about a cyclic descent extension for the promotion that we saw specifically, or for any?
No, there is a bijection. We do not know the bijection. This is existence theorem.
So if it's
existence, Bryce Wang illustrated one, let's say, twisted conjugated promotion that will prove this theorem combinatorially. Our proof is not constructive at all. Just say its existence. Okay.
One more question. So that need not be unique, right?
It's not unique for certain shapes. There is a paper when this is unique for shapes which are close to hooks. For hooks, there is no. For shapes which are very close to hooks, nearly hooks, it's unique. Okay. Significance of CD, let's go quickly.
Sorry, there's one more question.
Yeah. So just I started at 5+4. That's yeah.
Just to understand the cyclic descent extension definition, is there some example of a set and a descent function where the non-SCHR property is not true, but the other properties are true?
That which property? Non-SCHR, there are in the paper they are discussed. There are, but this is like esoteric examples. Okay. Significance of CD quickly. So it's enumeration thanks to due to non-SCHR property. There are very nice enumerative like cyclic Eulerians, etc. And twisted promotion by Wang. Cyclic descent algebra, cyclic quasi-symmetric functions algebra with Ira Gessel and Vic Reiner and Ronadin, and Postnikov-Turek Shark. In this talk, we will see connections to higherly algebras, characters, and they are geometric. It's related to Steinberg-Torus due to the works of Peterson and Stambridge, and to Gromov-Witten invariants due to works of Postnikov. So it's related to many branches in mathematics. Okay. So what is the problem that we will focus? Which conjugacy classes carry cyclic descent extension? Not, but Cellini is not working. Let's see an example. Cellini is not working. Let's take 4 cycles in S4. There are 6 4 cycles. What are these descents sets? 3, 1, 1, 2, 1, 2, 3, 2, 4, 1, 3. Is there any extension? Could we ad hoc? If we, let's say, not ad hoc, if we will see the cyclic, okay, this is Cellini, you see 4 here. So the only permutation, the only 4 cycle for which last letter is bigger than the first one is this one. So 4 appears only here. And this is not a cyclic descent extension. Why? Because if we see here 1, we should see 2. You know, it should be closed under cyclic rotation, the sets, and they're not. So this is not a CD. On the other hand, ad hoc, if we will add to all singletons the letter 4, then we will get a cyclic descent extension. But this is some misleading example. So in this case, we just add to the singletons. If we make all cyclic descents of same cardinality, many times it works, but mostly we could not do it because for most conjugacy classes, the range of cyclic of descent set cardinality or descent number is big. Okay, so this trick is not working. So anyway, the question is not easy. And to show the first sophisticated example, I thought it will take me 2 slides, so I will not show. Let at least S6 or whatever. Anyway, what is the main result? The main result is that a conjugacy class of cycle type mu has a cyclic descent extension if and only if mu is not of the form R to DS for some square free R. So, for example, if there are distinct cycles of distinct lengths, this is always okay. If not, n cycles, they should be square free. And R to DS, what's important is the R, that R should be square free. This is the result, and the proof is algebraic and involve higherly characters. And unfortunately, we do not have, even so I try to publicize this problem, find a constructive combinatorial proof. So now there is a progress, but not for this conference. So for involutions, we can do something on the spirit that was described by Tom Robbie, but not. So if we should combine Sheila Sundaram bijection from involutions to oscillating tableau and Stanley Chen and whatever, and and Dennis White ideas, and then we have something. The bijection is complicated, but we have like, we make it after complicated bijection. This is just rotation of certain web-like or even certain matching on the rotation clockwise or so, but this is after anyway. So this is just for involution. We do not know how to generalize our proof to other conjugacy classes. Maybe we can do block partition, like set partitions, but not anyway, partitions to blocks, but no conjugacy classes is very far from our horizons. So no combinatorial proof. Okay, so now I should go quickly. What is the main ingredient? Main ingredient in our proof? Our proof is proof of existence, not constructive. So we look on quasi-symmetric function. So the quasi-symmetric function, there is like what people call the quasi-symmetric generating function for the descent set of a conjugacy class. This is it's not a symmetric function. If you're not used to, so there is a language of characters. So there is the pre-image of this. This is n variables and the descent set. We like count. This is a generating function for the descent set over the conjugate. No, n is just to int. You can raise the n. That we take the n in each summand there are n variables. Just this. Just to enumerate. People do not write it for some reason, but it should be written because it's confusing. You have f sub b. What is b in what in subsets of mushroom? Subset of something. Okay. Now, okay. So there is a longer before it was this definition. Hierarchy character is the pre-image of this. This is a symmetric function. This is well known. And the pre-image is an induced character. So this is a sure positive symmetric function. And this is induced from one of the one-dimensional, like primitive, like you can think, linear characters of an element, of the centralizer of an element to the symmetric group. And this is the representation. And this is called hierarchy character. This character is the hierarchy character. And I would not go on classical result because it's important, but the hierarchy character, there is a 80 years old problem, very famous problem that many people walked about this, Kraskevich Weyman, Gessel Rotoner, Sheila Sundaram, Shoker, Vic Reiner and Hersch and Swanson, other people, about this, to decompose this representation, the hierarchy character into irreducibles. We know that this is true positive, so this is a proper character. It's not virtual. What are the multiplicities? We do not know. And to solve our problem, we should have some information on the multiplicities. And this is next slide. Okay, so we consider, this is for any set, but you can think the set to be conjugacy class. The conjugacy class A has a cyclic descent extension if and only if two conditions hold. We look on the multiplicity, the hook multiplicity is generating function in the hierarchy character, and it should be divisible by 1 plus x, and the quotient should have non-negative coefficients. And the easy part is the first part, the visibility is much easier. And this part is difficult for some conjugacy classes, you will see. Now I will go, okay. So the visibility, there are two. First of all, the hook multiplicity is generating function is divisible by 1 plus x if and only if the evaluation of the full cycle on this representation, the character of the full cycle on this representation is 0. And this we And we know that the hierarchy character on full cycles is if lambda is equal to R to the S is Mobius function of R, otherwise it's 0. You can, it's related to some classical results of classicals in algebraic combinatorics, some well-known results of Adrian Garcia and Michel Vax. So there is a combinatorial proof for this, and we give an algebraic proof for this formula. We give two different, one anyway. So this could be less than 1 page proof, so it's not so difficult. And this dilemma of divisibility on non-negativity also not so difficult. The difficulty is to prove non-negativity. Okay, if there are distinct cycles, there is a factorization lemma. If the partition is nu and R to the S, this here nu is free of parts of length R, then there is a factorization lemma which proves the divisibility and non-negativity after dividing by 1 plus x. These are generating function of Hooke multiplicities. So this is non-negative and this is easy part, the easiest part. Next, n cycles. Here we apply a formula of Shila-Sundaram for the sum, the multiplicity of the sum of multiplicities of two consequent hooks. And applying this, we can prove, it's not so easy, but we can prove that the multiplicities of the hooks are unimodal and sometimes also long concave. We will not speak about this, depending on the divisibility properties, but because they are unimodal, non-negativity follows. Anyway, the difficult part is R to the S, and I have not much time for this, but here, first we consider generalization of the Hooke multiplicity generating function. This is for, we fix R and round over S, and we take the sum of two. This is E sub k time elementary function, elementary symmetric function time homogeneous is the sum of two consequent hooks. Anyway, so this is it's easier to analyze this more complicated object. And if this more complicated object, if this has non-negative coefficients also, this has non-negative coefficient, and it's easier to prove that this has. How? By generalizing Sundaram. We generalize Sundaram lemma, and for not just Sundaram, he gave a very beautiful formula for the multiplicity of two consequent hooks in the Lie, no hierarchy, Lie character, which is n cycle. Like in code, now if we wanted to do it for R to the S, this is becoming much more complicated. The advantages of this formula that for the what we saw to be very difficult ER to the S, we have just multiplicative formula. And multiplicative formula, if you can analyze each of the factors and find that they are non-negative, then altogether it's non-negative and it's easier. So this is like 10, 15 pages proof. So this is the core and I really jumped over it. But let's come with some moral. I have 2 remaining minutes. So not moral, challenges. So first, all the moral is some people would not like is that you can do more with algebraic proofs than you can do with combinatorial bijections. Even so, they are more difficult and you should study a lot and you use lots of tools. At the end, if you have structure, the structure promises positive answers. Why it should be positive? Because there is some representation behind. But there should be combinatorial, like more elementary, or that easier to explain with beautiful and visual, like visual art. We said, like to come to museum. There is, if I would like to see something that you just rotate the elements in the conjugacy class and they look something like webs or something like I don't know what, and you rotate them and you get it, and you get the cyclic descent extension, but we do not have, and the difficulty is R2DS. Also, not half combinatorial is a proof that this, for any partition lambda, the Hooke multiplicity is generating function of the in the hierarchy character is unimodal. One can translate it to purely combinatorial statement. This says that if you measure, you count how many elements in the conjugacy class of cycle type lambda has cyclic descent prefix of length k. There are papers of Tibon about this, and so, but they did not give the information that we want. If you can prove that for any conjugacy class lambda, the number of elements having descent set prefix of length k is unimodal, this is a shortcut for a proof, then it will show that 15 pages of algebraic computations are needless, maybe important for the algebra, but not really needed here. But we cannot do it just for n cycles. We can the shortcut works. Okay, so thank you for hearing me. Sorry for being late of time.
Maybe just one quick question, if anybody has. If not, let's thank. Oh, sorry.
Quick question was just if you had a generalization for the multiplicity of, instead of a hook, a product of two.
Generalization of the multiplicity.
A multiplicity with a partition with two rows.
For so we didn't try two rows. I think for hooks like one cycle, k cycle, one can do it, but it's you do it for n cycle and you also distinct, so you combine. So this will give. So for hooks we can do it. For two rows we did not try. So. And I believe it could be that for two rows it will be easier to prove unimodality. But we did not try. Okay, thank you.
Thank you.
He said that he forgot one time the mic with him, and he went to his seat and he said the audience didn't understand anything. So I must say that the audience was responding, and I was happy with questions.
Thank you.